Hey everyone, I'm Jamel Balante. Today we're diving into this UML diagram that outlines a robot assembly system. Let's walk through it step by step so you can see how all the parts come together to build a functioning robot. This is where everything starts, the robot assembly line. Think of it like a robot factory. It has method called build robot, which take a bunch of inputs like the robot's name, eye color, power source, strength level, and even the weapon type. These details are used to build a custom robot. Once built, the robot is called. It creates a robot object. This class represents the final product, your full robot, made up 6 key parts: a head, torso, arms, legs, a weapon, plus some basic identity info like its name and model number. Each of those parts, head, torso, arms, legs, and weapon, is represented by its own class, and all of them inherit from a common abstract class called parts. That's important because it guarantees that every part can be activated. Here's the trick: parts is an abstract class. That means it defines a contract, in this case, an activate method which every part has to implement in its own way. This ensures the robot's components can be powered up and ready for action. For example, the head has an eye color and a sensor type, and it can scan areas. The arms store a strength level it can be activated. The torso holds the power source. The legs are responsible for movement, and the weapon defines how robot attacks, with both a type and a power level. Once all parts are created, they're passed into robot object using the assemble method. Now, the robot is completely and ready to act. The robot can then power up, activating all its parts, and move using its legs, in combat, engaging its weapon system. And if you ever need to access the finished robot, just call get robot on the assembly line. And boom, your custom built machine is ready to go. So that's how this robot assembly system works. Step by step, it's a clean modular design that makes it easy to build and control intelligent robots from usable parts. Thank you.
Hello everyone and greetings and welcome to our in-depth presentation on the robot assembly system. So I'm Mark Justin Alcantara and I'll kick things off by diving straight into the foundation piece of our code, the parts abstract base class. So we'll go line by line, unpacking not only what each bit of codes does, but why it's structured that this way. Then before we jump into the code, so let's set the stage. In this system, we simulate a futuristic factory that assembles robots from five essential components: head, torso, arms, legs, and weapon, showcasing composition in object-oriented programming. So each piece has its own attributes and behaviors, yet they all share one common contract. They must be able to activate themselves. So this is perfect use case for an abstract base class in Java. So which brings us to our first file, the parts.java. So here's the code. Here's the entire parts.java file. It's compact, just 5 lines, but it sets the contract for every robot part. So let's unpack it. So here, we declare an abstract class named parts. So why we declare this? So we want to enforce that every specific part, head, torso, etc., must share a common behavior, namely an activate method. And without providing a direct implementation here in this file. So by marking the class abstract, Java prevents us from creating a plain new parts instance. So it becomes a like a template only. So think of it like we're making an analogy here, like a recipe card. So obviously we cannot eat a recipe card, but every specific dish we cook follows that recipe's outline. So then we declare a abstract method here, activate, that returns nothing. So we're saying every subclass must provide its own implementation of activate. So this captures polymorphism. So we can call activate on any part's reference and the right behavior will run. So the public keyword ensures any part can be activated from outside. So abstracts this keyword tells us that the compiler there's nobody here. Then so what happens if we omit this abstract? So if we omit this abstract, you'd need to supply a method body. So if we change also the visibility to protected, for example, parts could be activated by the assembly line outside the package. So which is not the case here because all of this is just in a one package. Then so that's what wraps up the my deep dive in the deep part space class. So we've seen how this small file sets up the contract. Our golden rule that every component of the robot must have activate. So next up, my groupmate Almin Agaid will take you through the heart of our system, the robot class itself, where composition and polymorphism come together in harness. Over to you, Boy.
Go. Hello everyone, I'm Almina Guide and in this segment we're going to discuss the robot Java file where all of our parts come together under one roof. We'll look at how the class defines its identity, pulls references to each component, and uses methods to assemble, power up, and even engage in combat. So at the top, we declare public class robot. This makes the class visible to every other part of our application. Immediately after, we have two private string name and model number. This serves as the robot's unique identity. Below that, we declare five private fields, which is head, torso, arms, legs, and weapon. Each field is typed to its respective class so that once we assemble the part, we can store it directly in its slot. Ah, ulit. Here, we define the constructor. It takes the robot's name and model number as parameters and assigns them to the instance fields. Notice we do not initialize any parts yet. That happens later. This approach ensures that every robot object is created with a clear identity right from the start. The assemble method takes any object that implements parts and prints assembling it, then uses instance of checks to determine the actual subclass. Cast the part, assign, assigns it to the appropriate field, and print a confirmation message. This single method handles all five parts types, demonstrating polymorphism, one method, many possible part objects. Next is the power up method. Prints powering up, then checks each part in turn. If the part exists, we call its activate method. Otherwise, we print a warning message. This guarantees that only assembled components receive activation calls. So the next one is combat and movement. So the combat method switches the robot into combat mode, activates the arm, reports their strength, then activates and fire the weapon. After that, the move method prints prints a message showing movement speed based on the leg's mobility level. Right now, it's a simple print statement, so later we could extend it to animate or calculate actual movement. So the next reporter is Mark Joseph Taduran. Hi everyone, I'm Mark Joseph Taduran, and in this segment we will explore the two of our key components classes, head.java and torso.java. We'll see how each extend the parts based on classes, initialize its own attributes, and implement activation behavior. Let's pull up the code for head.java first. And now let's examine torso.java. It follows a similar pattern but focuses on power distribution. At the first part, public class torso extend part, like head, torso inherits the abstract construct to implement active and can also add its own behavior or properties. And next, private string power source. This represents the core energy supply for the robot. Example might be fusion core or battery pack. And next, public torso string power source takes a single argument and assign it the field by doing this at construction time. Every torso knows exactly what the power the robot entire system. And next, let's talk about override. Um, in this body activate, we print robots torso activated plus torso internal system powered up and energy is now distributed. This message indicates that the torso has come online. Its internal circuitry is activated and the power is flowing out to the other part, which the single method calls power up. The torso rides the entire robot for operation. And next reporter is talk about arms.java and legs.java. The reporter is Twisa Clarence Lloyd. Twisa Clarence Lloyd. Ano ba yun? Okay lang. The file begin with public class. Ito nga. Papakilala pa pala ako. Greetings everyone. I'm Clarence Lloyd Twisa and we discuss the class arm. The file begins with public class arm extend parts. This declaration tells Java that arms inherits from the abstract parts class and must implement the activate method. Next, we see the private field named strength level. This double the represent how powerful robots' arms are expressed as percentage or relative metric. The construction takes a single parameter, strength level, and assign it to the instance field. This ensures that every arms object is created with a defined power level. Current strength level. Other classes, such as robot, will call this method to determine how forcefully the arms can operate during combat or heavy-duty tasks. Finally, the activate method is overriding print a message indicating that the arms are powered up and primed for action. When power up called, this method we confirm that the arm's internal motor and the hydraulics are now engaged. That covers our walkthrough of arms.java. We've seen how the class stores and provides its strength level, and how it signals readiness for combat. Next is Brian Laderas will explore Legs Java, where we will define mobility and enable the robot to move. Greetings and hi everyone, I'm Brian Laderas and this segment will examine Legs.java. So we'll see how the class defines its mobility capabilities, provides movement, functionality, and implements activation behavior for our robot's legs. And here is the complete legs.java file. We'll step through each section to understand how it supports the robot's movements. The file begins with the class legs extends to parent class parts. Um, this declaration shows the legs inherits the abstract contract from parts, requiring an implementation of activate method. Next is the next is there is a private field mobility level of type double. This field represents the robot's speed or agility percentage. Then the contractor accepts a mobility level parameter and assign in the instance field. This ensures every legs object has defined mobility level upon creation. Then the move method. The move method prints a message indicating the robot's current movement speed. This method separates locomotion behavior from activation. And next is the getter method. The getter method is public double get mobility level. The get mobility level method returns the mobility level so other class like robot can reference to robot speed when needed. And the override activate method. So finally, the active activate method prints a message indicating that the legs has been powered up. When power up calls this method, we can confirm the legs actuators are now engaged. And so far, we now covered legs.java. So it inheritance, mobility attribute, movement method, accessor, and activation behavior. So the next speaker, Lloyd Tenorio, will guide you through weapon.java, where we'll explore weapon types, power levels, and attack functionality. So see you in the next segment.
Hello everyone, I'm Lloyd Ravi Tenorio, and in this segment, we will examine the weapon.java class. We'll review how it defines weapon attributes, provide attack functionality, and implements activation behavior. So this is the code. First is the class declaration. This declares the weapon class as a public and indicates that it inherits from the parts abstract class. By extending parts, weapon must implement the activate method and can define its own methods. Next one is the two private fields. These two private fields store the type of weapon and its power level percentage. The weapon type string identifies whether the robot uses a laser, missile, or other types of weapon. Next one is the double power level. Double indicates the weapon's current readiness strength. So how do we instantiate this class? We have the constructor, obviously. The constructor accepts two parameters, the weapon type and the power level. And then after that, it assigns them to the private instance fields. This makes sure that every weapon that is created with its type and power level defined. Next, the attack method. The attack method prints a message indicating the weapon, the type, and its power level percentage. This method simulates the robot executing an attack with its weapon system. So for example, laser attack. Power level is set to 30%. Last but not the least, the activate method. This method prints a message indicating that the weapon system has come online and it's ready. When the robot class power up method calls the activate method, this message confirms the weapon's internal systems have powered up successfully. Example is weapon system activate and ready for use. Lastly, this completes our detailed exploration of weapon.java. We saw how the class defines its attributes, implements the attack method, and overrides the attack activate. For readiness confirmation, ulit. This completes our detailed exploration of weapon.java. We saw how the class defines its attributes, implements the attack method, and overrides activate for readiness confirmation. In the final segment, Angelo Villanueva will present the main.java class, showing how we tie everything together to build and deploy our robots over to you.
Greetings. I'm Angelo Ryan D. Villanueva, and in this final segment, we'll walk through the main.java file, which serves as the entry point for our robot assembly system. We'll see how the program gathers user input, constructs the robot through the assembly line, and then powers it up. Let's dive right into it. So, first, we've uh, we've created a scanner object named input. So this will help us to gather user inputs that will be needed in building a new robot. Next, we instantiate the robot assembly line named new robot, which will coordinate the creation and assembly of our robot components. So the next part, we'll have the robot assembly system part. So in this part, you'll be entering robot information with regards to the parts of the robot. So in this first part, we'll first gather the needed arguments or values for the robot's head. So the system will ask for the user's input for the robot's name and then for the model number. So this part So this part will cater the creation of the robot object. So this is the constructor for the robot object. So next, we'll now move on to the creation or gathering of information for the robot head object. So in the robot head object, we'll be needing arguments for the eye color and the sensor type. So in this part, the system will ask for the robot's eye color and then for the sensory type. Now next, in this part, the system will ask for the information for the creation of the robot's torso. So for the torso, this program or the torso constructor will be needing an argument for the power source. Next, in this part, the system will ask for the values that is needed for the robot's arm specification. So under the robot's arm specification, it will be needing inputs for the strength level of the robot. Moving on, to complete the robot's legs specification, it will ask for the mobility level. And then lastly, for the robot weapon, it will ask two values, which is for the weapon type and the for the power level. So after that, after gathering all the necessary information for each part of the robots, for each of the robots needed parts, in this part, the new robot, that build robot, name, model number, eye color, sensory type, power source, strength level, mobility level, weapon type, and power level, this part, it will access the build robot method from the robot assembly line, so that the system will uh, store the data and at the same time create the objects for the robot's parts. Now, lastly, the method for the new robot, or the code block for the new robot that get robot, that power up, this line of code will call out that power up method from the robot class. So the power up constitutes the activating of the each parts of the robot. So it's this part. It will includes the activate method for each robot part classes that has been mentioned in the previous presentation. So this is the part of the power up method. So in this part, you'll observe that there would be an if else statement that will check if there's an existing object for the corresponding robot part. So you have here head, torso, arms, legs, and then weapon. So if the object is not equal to null, the activate method will be done. But if the head object is equal to none, or there's no existing head object, there would be print. There would be a error message that will appear at the console. So that is it for the main.java file. Thank you for listening.
So, Dangal greetings. My name is Josh Russell R. Pamintuan. So, now let's walk through the output of the program. So, the system begins by asking the user to enter the robot's name and the model. So, let's say the robot name is Titan. And then enter robot model number. For example, is TK9. And then next, the user input is specification for each robot parts such as eye color, sensor type, power source, strength level, mobility level, weapon type, and weapon power level. So let's enter robot eye color. For example, is red. And then robot sensor type is infrared. And then robot torso specification. So enter robot power source. For example, is a battery. And then robot arm, enter a robot strength level. For example, is level 10. And then robot legs specification. So enter robot mobility. Let's say 50. And then robot weapon specification. Enter robot weapon type. For example, is cannon blast. Enter. So the level is 15. Let's say 15. Enter. So this is the final output. Once all input are gathered, the assembly process begin. Each part is assembly one by one, and the system confirm each successfully attachment. Okay, thank you.